actually these excitation tables, okay, excitation tables are regarding the exact reverse information to your truth tables, guys. These truth tables will give you the information about the next state with the help of present input and current state will give you the next state or output what we have. Whereas guys, if you go for the excitation tables, these excitation tables will give you the information regarding what set of informations or input we should have for the given present state and next state. Okay, the information regarding the present state and next state will be available with us, and for those informations what set of inputs will be exactly perfect matching for those informations is to be found. That is possible with the help of excitation table, guys. These excitation tables are helping us to convert one flip-flop to another flip-flop. Okay, if you're having SR flip-flop or JK or D or T, to convert this flip-flop to another flip-flop, we need these excitation tables in design part, guys. Okay, so in designing or converting one flip-flop to another one, we definitely need we definitely need these excitation tables, guys. Okay, these excitation tables are very important. Then guys, I hope you all guys very well know about the truth tables what we have. Okay, truth tables what we have for all the flip-flops including SR, JK, T and D flip-flops. Okay guys, I'll be asking randomly, okay, some students regarding the about the truth tables what we have for all the flip-flops. You got to say me, guys. Otherwise, unless otherwise you know the truth table information regarding all the flip-flops, okay, these excitation tables will be very difficult to understand, guys. Once just open SR flip-flops truth table. Just open SR flip-flops truth table. Have you opened it, guys?
Yes, sir.
Yes, sir.
Yeah, if it is okay, then let us go here, guys. In the truth table of a SR flip-flop, we'll have a initial thing called clock. Okay, then clock is followed by the two inputs what we have in SR flip-flop are set and reset inputs, then which is followed by the present state Q or QN what we call, which is followed by next state Q of N plus 1. Guys, all of you open the truth table what we have for SR flip-flop, then we can easily understand. Okay, Q of N plus 1, and we'll be naming what state it is lying it. Okay, what state it is going to be presented. Okay, now guys, let us assume that we are going with a positive edge triggered SR flip-flop. And what is the first input combination, guys? What is the first input combination? What is the first
Zero,
input?
zero.
Yeah, 0, 0. And let us assume that our present state is also 0. Then if your SR flip-flop is given with 0, 0 input, what state it will move automatically, guys?
No change.
No
No
change.
change, sir.
No. Yeah, thank you. No change means what, guys? No change means what? What will be your output state? What will be your output state? What will be your next?
Zero, sir.
Taken in present?
Yeah.
Present input.
Yeah, present state will be directly taken as next state. So I'm getting 0 here. Then the same combination with a different present state I'm taking now, guys. 0, 0 is my input and my present state is 1 now. Okay, then my next state also 1 since it is no change state. Your first input combination is completely over, guys. Let us go for the next one. That is, I'm taking my inputs 0, 1 now. Okay, I'm taking my input 0, 1. Okay, and the same 0, 1 should be taken for different present state condition. Okay, 0, 1 and 0, 1. When my present state 0, present state 1 is to be found here, guys. Okay, guys, tell me, if I have my present state 0 with the input 0, 1, what should be my output state, guys, or next state?
0.
0. Okay,
sir.
0 always. Why, guys? What state it will be?
Reset state, sir.
Yeah, we are going for reset state. Okay, your second set of combination is over. Now let us go for the third set of inputs. That is 1, 0 we will take, guys. Okay, 1, 0 when my present state 0. Okay, and the same 1 0 with my present state 1 is to be found, okay, is to be calculated. Then tell me guys, what will be your next state in this case? What
One,
is-
sir.
One, sir.
One in here, okay. So one is your output and the state is set state, okay, set state.
Set state.
Yeah, let us go
Set
for the last
state.
one, guys. Let us go for the last one, okay. So that I'm going for 1 and 1, okay. 1 and 1 is my input combination now, okay. So when 1 1 is there, okay, and when present state is 0 and present state is 1 is also is to be found, okay. Okay guys, so that is my input present state combinations. Tell me guys, what will be your next state or next state output you'll get here?
Don't care condition.
Yeah, don't care.
Send it.
Yeah,
Care
we don't know.
conditions, sir.
Yeah, we don't know what will be your next state. So we are writing don't care condition, and we name this state as indeterminate state. Okay. Yeah, indeterminate state, guys. Okay. So this is the truth table what we have for a SR flip flop, guys. Okay, with the help of clock. Okay, now keeping this truth table information with us, we got to design the excitation table for this SR flip-flop. Okay, guys, look at here. I'm going to explain what we are doing in truth table with the help of input combinations, with the help of present state what we have. Okay, these two information are available with us. With these two informations, okay, we have concluded or we found what is the value of this next state qn plus 1. That is what we have done in truth table. Okay, we have input, we have present state. With these two informations, we found what is our next state. Whereas in excitation table, it is exactly reverse, guys. Exactly reverse. Like we will have our present state value with us, that is qn, let us name, and we will have what is our next state also. Okay, what is our next state? Here we'll have these two informations with us, and by using these two informations, we got to find what combination of inputs will match that condition. Okay, by taking which set of input combinations we can match this combination, we have to write. Let us see, guys, we have truth table clearly with us. Let us go and see. First of all, guys, I am taking the combinations here: 0 0 0 1 1 0 and 1 1. Okay, 1 1. This is the combination I am trying to take here to explain the excitation table of a SR flip-flop. Okay, this is how the excitation table look like, guys. We have to take what is our present state, what is our next state, and fill the information of combination of inputs. Using these combinations, we got to write what inputs will match this combination of present state and next state. Okay, that will give you the excitation table. Okay, excitation table. Okay, excitation table for SR. Okay, for SR flip flop. Okay, SR for SR flip flop. Okay, look at here, guys. Look at here. Look at here, guys. We have present state, we have next state as 0 0 initially. Guys, look at the truth table what we have in the left side. Okay, look at the truth table on the left side. We have present state 0 here and next state also 0 here. Okay, present state 0 and next state 0. Then which combination out of all these states having present state 0, next state 0 here, present state 0, next state 0 combination, how many are there? No, look at here. What I'm listen here. What I'm saying, I have present state 0, next state 0 here. How many combinations are there like present state 0, next state 0? This is your present state 0, next state 0.
Two combinations, sir.
Present state 0, next state 0. Yeah, there are two combinations matching our present state 0, next state 0 combination. Look at their inputs now. This is first combination, present state 0, next state 0, first combination. Here, what is your inputs, guys? What is your inputs?
0 0, sir.
Yeah,
0 0.
Yeah, let me write the first combination. For the first combination, okay, when I'm writing my present state and next state values like qn and qn plus 1, okay, qn plus 1 I'm writing as next state. Okay, So for the present state 0 and next state 0, the first combination is input combinations is 0 0. So I'm writing that. And for the same present state 0 next state 0 combination, another input combination what we have is 0
0 1 sir.
1. Okay, so in this SR truth table, for the combination of present state 0 next state 0, there are two input combinations available. One is 0 0, another one is 0 1 in here, guys. In both the combinations, what are the values of S? What are the values of S here, guys?
Both are 0 0
Both
sir.
are 0. So
Zero.
under S you write
Both are
0.
zero,
Yeah.
sir.
Yeah. So under S you write 0 here. And what about R here, guys? What about R?
0 1 sir.
0 1.
Zero.
So
0 and 1.
yeah. So what you should write here is don't care, because at one condition you have 0, at another condition you have 1, such that you cannot decide your R should be 0 or 1. You cannot decide whether it should be 0 or 1. In such a case, you should take don't care under R. Guys, do you understand how I have written this first combination?
Yes sir.
Yeah, likewise, I'm not going to explain this. You have to say this to me. Looking at truth table, how many combinations do you have with present state 0, next state 1? Present state should be 0, next state 1. Look at the present state 0, next state 1.
1, sir.
One only sir.
Only, yeah, only one combination is available. Okay, only one state, one combination is available. For that, what is your input combination?
1
1
0.
comma 0
So,
sir.
yeah, directly take 1 0 under S and R. Okay, now go for the third one. Your present state 1, next state 0. How many combinations are there?
Only 1.
1 sir.
Yeah, 1 0. Here it is. What is the input combination for that?
0 1.
Write that directly. Now go for the last combination, guys. You have present state 1, next state 1. How many combinations are there for that?
2 sir.
2 states are there. Okay, then look at the S value for those two. What are the input combinations you have for this 1 1?
0 0 sir.
0 0 is one
0
combination.
0 0 1 0.
And 1 0 sir.
1 0.
Yeah. What is the value of S?
Don't care on 0 sir.
Yeah, you have to write
Condition, sir.
0. Don't care is the value of the S, and you can see R value remains 0 in both combinations. So I can write 0. Guys, this is called the excitation table of SR flip-flop. This is called the excitation table of SR flip-flop. Guys, do you got an idea how to write the excitation table of SR flip-flop?
Yes sir.
Yeah, like this, we got to design the excitation table for D flip-flop. We had to write for JK flip-flop. We had to write for T flip-flop, toggle flip-flop, guys. Okay, all these things should be there in your mind. So if you want to write the excitation tables, you should definitely have the information regarding all the truth tables what we have for all the flip-flops. Guys, can you write the excitation table without knowing truth table? Is it possible?
No sir.
No, not at all possible. You should have a clear-cut idea what you are going to have in SR truth table. Then only you can write excitation table for corresponding flip-flop. Okay, that is what the case in here. Okay, now guys, with this information, let us go and see. Okay, let us go and see the excitation tables for remaining flip-flops. Okay, now we have seen what is a truth table of SR and excitation table for SR flip-flop. Now, one more thing we should know here in SR flip-flop is its characteristic equation, guys. Okay, it's characteristic equation. Okay, look at here, guys. You should remember this forever. Okay, and you should remember this forever. These are also very important later. Yeah, guys. Someone please mute your voice. Someone is talking here. Please mute your voice. I think Banu Prakash. Banu Prakash. Yeah, guys, okay, let us go here. Yeah, we are looking at a characteristic equation for SR flip-flop. That is, you should remember, guys, note it down. The characteristic equation will give you the relation between the output, means next state, and the present state and inputs, guys. Okay, how you're getting your next state with the help of present state, and your input combination will be given by characteristic equation, guys. How you're going to find this? Draw a truth k-map, draw a k-map or design a k-map for these values. Okay, then you can easily understand how you're getting this characteristic equation, guys. Okay, so the characteristic equation for SR flip-flop is Q of n plus 1 is equal to S plus R bar into Qn. Okay, S plus R bar into Qn is a characteristic equation for SR flip-flop. Guys, have you noted down? Have you noted down? Q of n plus 1 is equal to S plus R bar into Qn is the characteristic equation we have for SR flip-flop, and you already have already shown how to design the excitation table for SR flip-flop is completely over, and this is the truth table what we have for SR flip-flop. Guys, let us go for the second one, that is JK flip-flop. JK flip-flop. Okay, so here you can see the basic block diagram of JK flip-flop, and this is the truth table or characteristic table for JK flip-flop. Guys, look at, guys, what happens in JK flip-flop? What happens in JK flip-flop? When I'm giving 0, 0, what state you will move to? In JK flip-flop, if I give J equal to 0, K equal to 0, what state you will move to, guys?
No change.
No change state means what is your present state? Always your present state is next state. Okay, so what is your present state? That will be coming as next state. So when J equal to 0, K equal to 0, your next state Q of n plus 1 is equal to Q. That is nothing but present state, guys. When I'm giving 0, 1, what state we call in JK flip-flop? 0, 1. J equal to 0, K equal to 1.
Reset state, sir.
Reset state. So output is 0 here. When J equal to 1 and K equal to 0, what state it is?
Set state, sir.
What will be the output at that case? What will be the output?
1, sir.
1, you can see, guys. Okay, now when I'm giving J equal to 1 and K equal to 1, very important case in JK flip-flop, when I'm giving J equal to 1 and K equal to 1, we move to toggle state. Okay, we move to toggle state. So I'm getting the reverse of present state. Q bar is shown in here. Q bar is your toggle state, guys. That is what is occurring in JK flip-flop. 0, 0, no change. 0, 1, reset. 1, 0, set. And 1, 1 is toggle. So I'm getting Q bar in here, guys. That is your truth table. And the characteristic equation, from this characteristic table, I'm going to design the characteristic equation in here. Okay, with this characteristic table, I'm going to design characteristic equation. In this, the characteristic equation for this JK flip-flop is Q n plus 1. That is nothing but next state is equal to J K bar, J Q bar plus K bar into Q, guys. Guys, you can easily design this characteristic equation using the circuit diagram what we have for JK flip-flop also. You have feedback connection from Q bar to the first input J, and second feedback line from Q to K. So if you multiply those values and add J into Q bar plus K bar into Q, you will get feedback lines from output to the input in JK flip-flop. That is what they have shown. J into Q bar plus K bar into Q is the characteristic equation we have for JK flip-flop. And look at here, guys, how you're writing excitation table. I have 0, 0 as my present state and next state combination. Look at the truth table and say, so wherever I can get 0, 0 as my present state and next state, wherever I can get present state, next state 0 for the combination. 0, 0 is one combination.
0, 0, sir.
Okay, 0, 0 is one combination, and I think that is only the combination I can get. And is there anything else? Is there anything else we can get for JK flip-flop? Look at your truth table, detailed truth table what we have for JK flip-flop. Detailed truth table I have given for JK flip-flop. Look into that. In which combinations we can get both your present state and next state values as zeros. Look at there, guys. In which combinations I can get present state and next state both as 0. One is no change state. one combination. Okay, for the no change state, I can get both your present state and next state 0, and like that I can get for reset state also. Okay, I can get for reset state also, I think. Check out. So I'm getting 0 on don't care condition for J and K, guys. Okay, so let us go for that. I will explain that with clear cut information, guys. Look at here. So this is your JK SR flip-flops truth table. With the same information, let me explain you how your JK flip-flop is going to look like. Okay, so guys, with the same information, I'm trying to design excitation table for your JK flip-flop. Let us look at here. So I'm taking J and K as my input variables. Okay, J and K as my input variables. So guys, your first 3 states will be remain same in the case of no change state and reset state and set state. For these 3 states, both SR flip-flop and JK flip-flop remain same. Only for the last condition, when I'm taking J equal to 1 and K equal to 1, the state it is moving will be changing. What state we call when I'm giving J equal to 1 and K equal to 1, guys? Tell
Toggle
me.
state, sir.
Toggle state. So
Toggle state.
toggle state means if your present state is 0, what will be your next state, guys?
Complement
Opposite
inverse
sums.
1,
Yeah.
sir.
So if
Inversion,
I'm
sir,
giving
one,
my
sir.
present state as 1, your
0, sir.
next state is
0,
0,
sir.
guys. Okay, so keep this in the mind. Keep this in the mind. We'll design the excitation table now, guys. So I'm taking Qn and I'm taking Qn plus 1 as my next state. Qn plus 1, guys. And I got to design what are my input combinations that will exactly support these combination of present state and next state. So I'm taking J and K here. Okay, J and K here, guys. Now take the combinations 0, 0, then 0, 1, then 1, 0, and 1 and 1. Okay, so I have taken all the combinations what I can take for the design of an excitation table. Now guys, look at there and tell me, look at the detailed JK truth table you have here. Look at the combination of 0, 0, where it is available. Present state 0, next state 0. Okay, this is one combination and this is one more combination you have here, guys. Okay, this is one combination, present state 0, next state 0, and this is also second combination I have for present state 0, next state 0. Then tell me what will be your J and K values here.
0 and don't care.
0 and don't
Yeah,
care, sir.
0, don't care. Now, yeah, now go for the next case, 0, 1. Present state must be 0, next state is 1. So this is one case. Okay. Yeah, is there anything else like, yeah, one more combination is available in here. Present state 0, next state 1 case. Okay, so look at these 2 cases and tell me what will be your J and K values.
1 don't care.
Yeah, clearly guys, that is exactly right. 1 and don't care. Yeah, let me take 1 and don't care as your excitation table values. Then go for the next one, guys. Next cases where I can get 1 and 0. Where I can get 1 and 0 as my next combinations. Look at 1 and 0 combinations. This is one combination.
Only 1, sir.
1, 0. This is the combination. Yeah,
1,
this
0
is,
and 1.
yeah, there are 2 cases. Now look at these 2 cases and tell me what must be your JK values.
Don't care and
Don't
1.
care and 1, sir.
Don't care condition and 1.
Yeah, don't care and 1, clearly guys. Now let us move to the last case, that is present state 1, next state 1. Look at those cases, present state 1 case and next state 1 case. Present state and next state both should be 1. This is one case.
2 cases, sir.
Yeah, and one more you have in here. And look at the input combination for those 2.
0, 0 and 1, 0, 7.
So
Don't care and 0, sir.
don't care and 0. Okay,
Condition, sir.
0, don't care and 0. Okay, guys, this is the excitation table we can design for JK flip-flop with the help of truth table we have. Guys, this is exactly reverse case. That's it. With the help of inputs and present state, if you design your next state or decide your next state, that is truth table. With the help of present state and next state values, if you design or find what will be your input combination suitably, then this is called excitation table, guys. Okay, have you noted down the excitation table for JK flip-flop? However, I will
Yes, sir.
yeah, however, I will send that PPT. However, don't worry. Then guys, this is the characteristic equation we can have for JK flip-flop, that is J into K bar plus K bar into Q. And let's move to the D flip-flop, guys. D flip-flop. Now you got to say, take the D flip-flops truth table. Guys, I told you clearly, there is only one condition in D flip-flop. Whatever the input you are giving, that will be shown directly as your output. Okay, so your input D is always is equal to our next state Q of n plus 1. Okay, both input and output are same, and that's why it is called delay flip-flop or data flip-flop. Whatever the input you are giving with some delay will be shown directly at your output. So look at the characteristic equation what they have shown. Your next state is equal to input. Okay, input and output both are same. And that you can see in a truth table also. D is your input and Q next is nothing but the next state or output. If input is 0, output 0. If input is 1, output is 1. Both are same, guys. That is why it is called delay flip-flop. And the characteristic equation also same, showing the same. Your next state and input both are equal. This is the characteristic equation, guys. This characteristic equation also very important later in the design part. So you should definitely remember and note down the characteristic equations what we have. Then let us go and see the excitation table what we have, guys. Excitation tables. Take your present state and next state combinations 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 1. Guys, you can directly say no need to go for the truth table. Actually, what I told about the truth table about the D flip-flop, always the input is equal to what I told you about the truth table, guys. Input is always is equal to
Output.
Okay, whatever the input you are giving, directly that will be coming in output. So in your excitation table also you have present state and next state. This is nothing but output. That output can be directly taken into the input. 0, 1, 0, 1 is your output. The same 0, 1, 0, 1 you can see in your input also, guys. Okay, no need to go for the truth table. If you understand, D flip-flop will give you both input and output values as same. So your next state will be directly equal to input condition in here. So guys, any doubts in the excitation table of D flip-flop? Next state is equal to input. So directly I'm writing those values. Any doubts still, guys? Students, any doubts in this excitation table I'm asking? If you say okay, then I will go for the next flip-flop. Guys, can you hear my voice?
Yeah, okay, sir.
Any doubts in the excitation table? Any doubts? Or do you
No,
need
sir.
to go? Do I need to go for whiteboard and I have to explain again the same concept with the help of D for the D flip-flop? Or do you understand this one directly? Do you understand this directly, or do I need to go back to whiteboard and I got to explain this?
No need, sir.
Yeah, no need. Then go. Let us see the last flip-flop and its excitation table, guys. You can see the block diagram of T flip-flop and its truth table. Guys, you already know in T flip-flop, we can give either T equal to 0 or T equal to 1. If I'm giving T equal to 0, that state is called no change state. Means your next state is equal to present state. That's why they have given Q next is equal to Q, nothing but present state. Next state is equal to present state. And next one, when I'm giving T equal to 1, that is called toggle state, you will get the inversion of present state. So they are writing Q bar in here. That is a truth table we can write for T flip-flop. Using this information, they are trying to design the characteristic equation. Output Q next is equal to T into Q bar plus T bar into Q is your characteristic equation, guys. And note it down, T into Q bar plus T bar into Q is the characteristic equation. Almost the same kind of characteristic equation you can see in a JK flip-flop also. J into Q bar plus K bar into Q is the characteristic equation you can see in there. Because we have designed the T flip-flop by modifying some little things in JK. So almost this JK flip-flop and T flip-flop remain same in two states what we have here. Okay, look at here, guys. I'm taking different combinations of present state and next state to design the excitation table here. 0, 0, 0, 1, 1, 0, 1, 1 combinations for present state and next state. And guys, you already know, always if your present state is if your input is 0, then your output is exactly the same as your present state. Okay, output is exactly same as present state. And if input is 1, then you're having toggle state, you're going to get exactly reverse of your present state. So by toggle condition, you keep that those 2 points in the mind, and we can easily design this excitation table here, guys. Look at, guys, look at the truth table. This is next state and this is present state. Both present state and next state are same when your t is equal to 0. So look at here, when present state and next state both are same, it is called no change state. That is happening when I'm giving t equal to 0. So I'm writing input t equal to 0. And last case also, guys, present state and next state both are same when t is equal to 0. So I'm giving t equal to 0, guys. And present state 0 means next state 1, reverse of it. And present state 1 and next state is 0, means reverse of it. So in these two conditions, you can see toggle condition. In T flip-flop, toggle condition only occur when T is equal to 1. So I'm giving T equal to 1 in these two conditions. Guys, do you understand this logic, how I have designed this excitation table? In T flip-flop, there are only two combinations. One is no change state, another one is toggle state. No change state means your present state and next state are same. Look at here. In these two conditions, present state and next state both are 0. In this condition also, present state and next state both are 1. In these two conditions, there are no change conditions. So no change condition, input t should be 0. So I'm writing t equal to 0 and t equal to 0 here. In